Hello everyone, I'm Divyaksha Chima. Today, we're diving into what is arguably one of the most crucial and, let's be honest, often the most intimidating chapters of Class XII Chemistry, Electrochemistry. I know, this chapter can seem super overwhelming at first glance, but really, don't stress about it. In this explainer, we're going to break it down from the absolute basics, step by step. By the time we wrap up, I promise you, electrochemistry is going to feel so much easier and incredibly logical.
All right, here is our game plan for today. First, the basics of electrochemistry. Second, electrochemical cells. Third, the Nernst equation. Fourth, conductance and conductivity. Fifth, Faraday's laws. And finally, some essential CBSE exam tips.
Section 1. Basics of Electrochemistry, the foundation.
Okay, before we can build the house, we absolutely need a rock-solid foundation, right? In electrochemistry, that entire foundation comes down to one really simple concept: the transfer of electrons. To get this, you just need to master two words: oxidation and reduction. It's quite straightforward. Oxidation simply means the loss of electrons, while reduction is the gain of electrons. That's it. That is the core of this whole chapter. If a substance gives away its electrons, it gets oxidized. If it snatches up electrons, it gets reduced. And since these two always happen together, we just smash the words together and call them redox reactions.
Now, I know that during the pressure of a big board exam, it is ridiculously easy to mix these two up. So here's my favorite little trick to lock this in your memory. Oil rig. Just think oxidation is loss, reduction is gain. It's a lifesaver. Keep that acronym in your back pocket. Whenever you're staring at a chemical equation and you're feeling a bit lost, just whisper oil rig to yourself. It'll completely save you from those silly, totally avoidable mistakes.
Section 2. Electrochemical Cells Explained, where the magic happens.
So, now that we've got electron transfer down, we need a physical setup where these reactions actually happen. Broadly speaking, we're dealing with two main types of cells, and they do the exact opposite of each other. First up, galvanic or voltaic cells. These guys take a spontaneous chemical reaction and use it to generate electrical energy. Think of the batteries powering your TV remote right now. On the flip side, we have electrolytic cells. These actually consume electrical energy to force a non-spontaneous chemical reaction to happen. Basically, galvanic creates the electricity and electrolytic uses it up.
Let's zoom in on the most famous galvanic cell of them all, the Daniell cell. There are a few key pieces here you absolutely have to know. We've got two electrodes, the anode and the cathode, and they are sitting in their own electrolytic solutions. These two halves are connected internally by a U-shaped tube called a salt bridge. This is super important because it maintains electrical neutrality. We also use a very specific shorthand called cell notation to write all of this out in a single line, so you don't have to draw the whole elaborate diagram every single time. Now, think about those two electrodes for a second. Do you know which one acts as the anode? Let me ask you this. If oxidation is the loss of electrons, and it always happens at the anode, in which direction will the electron flow actually happen? Just take a quick second to visualize the setup in your head. Where exactly are the electrons coming from, and where are they trying to go? If you guessed from anode to cathode, you hit the nail on the head. Electrons will always flow from the anode over to the cathode through the external circuit. Because the anode is actively losing those electrons, they travel straight through the wire right over to the cathode, which is just waiting there to gain them. This continuous flow of electrons is exactly what creates an electrical current, and the potential difference between these two electrodes, well, that gives us our standard cell potential.
Section 3. The Nernst equation, mastering the math. Okay, so we just talked about standard cell potential, but what happens in the real world when our concentrations aren't perfectly standard? Enter the Nernst equation. Now, I know this formula looks super intimidating, but please do not panic. We're going to break it down. Step 1. Always find your standard cell potential, your E0 cell first. This is usually just cathode minus anode. Step 2. Figure out your reaction quotient Q. That's simply the concentration of your products divided by the concentration of your reactants. Just don't forget your stoichiometry. And finally, step 3. Plug those values right into the Nernst formula. Boom, that's it. If you approach literally any numerical with these three clear, logical steps, you are never going to get lost in the math.
Section 4. Conductance and molar conductivity. Ions in motion.
All right, let's shift gears and look inside the cell itself. Electricity in these solutions is conducted by the movement of ions, and there are four major terms you're going to encounter here. First is conductance, represented by G, which is just how easily current flows. Then we have resistance, R, which is the exact opposite. It's the obstruction to that flow. Next is specific conductance, or conductivity. We denote this with the Greek letter kappa, and it's the conductance of 1 unit volume of your solution. Lastly, there's molar conductivity, lambda m, which is the total conducting power of all the ions produced by dissolving exactly 1 mole of an electrolyte. Getting these definitions crisp and knowing the exact symbols will save you so much precious time during your exams.
Now, tied directly to this is a really fascinating concept, Kohlrausch's law of independent migration of ions. Basically, it tells us that at infinite dilution, every single ion makes a definite, fixed contribution to the total molar conductivity of an electrolyte. And it does this completely regardless of the other ion it happens to be paired with. This beautifully explains how molar conductivity changes with concentration. Think about it. As you dilute a solution, meaning you drop the concentration, the molar conductivity actually shoots up. Why? Because the ions suddenly have way more room to move around freely without bumping into or interfering with each other.
Section 5. Faraday's Laws of Electrolysis. Quantifying the process.
So exactly how much chemical reaction is happening during electrolysis? Say, how many grams of copper are actually being deposited? This is where Michael Faraday steps in. His first law tells us that the mass of the substance deposited, or liberated, at any electrode is directly proportional to the quantity of electricity you pass through the electrolyte. Put simply, more current equals more deposit. Then his second law states that if you pass the exact same amount of electricity through different electrolytes, the masses deposited are going to be proportional to their respective equivalent weights. These two laws are absolutely non-negotiable. Any numerical that asks you to calculate the amount of a substance deposited is going to require you to apply Faraday's principles.
Section 6. CBSE exam formulas and tips.
And here we are at the final step of our staircase, turning all of these concepts into those high marks you absolutely deserve. Now listen, for your board exams, the most crucial thing isn't just blindly memorizing a page of formulas. It's about deeply understanding what the variables actually mean. For instance, if you truly understand that the little n in the Nernst equation stands for the exact number of electrons exchanged, you'll be able to confidently solve the problem no matter how they twist it. Rote memorization is only going to get you so far. True understanding is what actually fetches you those full marks.
As someone who has checked hundreds and hundreds of exam papers, I literally see the exact same mistakes crop up every single year. Please don't fall into these traps. First up, confusing anode and cathode signs. Just remember, while galvanic and electrolytic signs are different, oxidation is always at the anode, period. Second, forgetting units. Cell potential is in volts, conductivity has its own specific units, you have to write them down. And third, miscalculating that N value, the number of electrons. Always balance your redox half reactions before you even think about plugging N into the Nernst equation. If you just keep these classic pitfalls in mind, you are going to secure every single mark possible.
So, I want to leave you with this one question. Are you ready to tackle your electrochemistry numericals with total confidence? Because you absolutely should be. You now have the logical foundation required to master this entire chapter. As you go off and practice your past papers, just remember that you aren't just doing boring math. You're calculating the very same chemical magic that literally powers the world around you. Keep practicing, trust your logic, and I will see you in our next explainer.